Hi everyone, my name is Aleksandra Faust. I'm a research scientist in Google Brain, and today I'm going to share with you our recent progress on robot navigation in real world. In the United States alone, there's 12 million people, which is entire population of New York City and Los Angeles, that cannot leave their homes without any assistive device. Pandemic taught us that all of us can be in that situation, and having robots that can deliver goods, grocery items, food and medicine, and so on, can make a huge difference in all of our lives. But what is really that we need to achieve that picture? Well, we need autonomous robots at scale, in real world, on real robots. Uh, what do I mean by that? So let's look at this example here. We have a robot that we started at one point and it's trying to get to the sink, and we repeat this scenario over and over. There are people around, things are changing, environment is changing, and that is real world. Now we have a person standing here in front blocking the way, so robot needs to go around the table, person coming in. That is what we mean by real world. This is, by the way, fully trained, reinforcement learning policy trained fully in simulation and transferred in real world. Here we have a janitor. We did not stage this at all. So in this case, the robot observes the environment with a LiDAR sensor. It controls itself with the angular and linear velocity, and it just needs to get to the goal and deal whatever it needs to deal in order to get there. It doesn't need to know where it is environment, why is it going there, and so on. It just has a goal and needs to get there. On the other hand, we have robots, and robots come in all shape and sizes, and their sensors, their dynamics, their bodies, and even onboard compute determine their abilities. They determine how they move and what they are capable of, and what is exactly, all of them can go from A to B, but how they get from A to B, that motion varies very much. So, for example, the little quad rotor can fly overboard. The fetch robot and freight robots move on the ground, but freight robots, because it is shorter, can go under tables and so on. So we like to have safe and feasible motion in this dynamic world where they need to operate. And ideally, the same methodology that we can train any type of robot to perform to the best of its own abilities. So classical approaches generally do not scale. And classical approaches consist of the standard perception and SLAM, and then goes motion planning and control. It's modular, it's great, it does not scale. And the reason it does not scale, there are two reasons. There are many, but for the purposes of this talk, one is because as we kind of transfer between the robots and the environments, each layer does not know about the strengths and the weaknesses of the previous layer, and then we can design different heuristics to make them work. And the second reason it doesn't work is a classic pipeline treats every instance of the problem as a new problem. There is no method that takes the experience from all previous examples and so on and kind of summarizes them. That heuristics is called human engineer, right? But in terms of the classic pipeline, there is no learning. So, but we can do that. So can we borrow a book from biological systems and see how biological systems handle that? So just an example, one thing we know is that we always observe with sensors and we always express ourselves with emotion, and whatever happens in that box stays within box, right? So first thing that happens with biological systems is that the evolution determines what is the system capable of. It determines the hyperparameters of the system, if you wish, that is tuned to the environment and the tasks that the system is going to perform. Now, once we have the system, we then interact with our environments. This is my daughter learning to walk and interacting with the environment. And we practice the skill until we get better at it. And then finally, once we have some competency, we reflect on our experience and we learn from it. And we know how to predict in the future that certain things work or might not work, and so on. We call this intuition, but real intuition is our prior experience fit into a predictive model. So, can we learn some of this? Can we take the inspiration from the biological system and apply them to the robotics and navigation specifically and see how we go? So one thing that we first need to ask is what are the basic skills that we interact with the system, and then how that can be a building block for the larger, more complex things. So from that perspective, in the rest of the talk, we'll ask first question how to get to a goal, how can we learn these policies like we described earlier in the talk, where robot is just reacting and going from A to B, dealing with the real world. And then in the second part, we're going to talk about how we determine what the goal should be. In that case, the robot needs more context and so on. And the caveat here is that finding the goal not only needs to be optimal for the task that's being solved, but also needs to be feasible for the robot, for the competency of the robot. So the first question is how to get to a goal, and here we're learning the goal condition obstacle avoidance control policies. They don't need to know where they are, they just need to get where they need to get. And that kind of lends itself very nicely to reinforcement learning. And one way to learn that is that our robot, the observations are goal and the noisy lidar observations. The actions are linear and angular velocity, like I mentioned earlier. And then we train the environment in a small static environment. The key here is how to design the simplest environment that we can to have the zero shot transfer from sim to real. And then the objective or the reward should be whether the goal is reached or not. However, that is sparse, subjective, and not conductive to training. So we end up having to do lots of engineering to find the right reward that's conductive to that training. The second design choice that we need to make is around neural network architecture. And again, this is very human intensive process, and how to create a simulator, as I mentioned. So in order to get these policies to work easily and scalably, we first approach the automation of the rewarded neural network architecture. And the way we do this is it's a two-step process. The observation is, the insight is that for the rewards, learning intrinsic rewards is we have generally a good intuition what the relevant features of the intrinsic reward are, even though the objective is sparse. So in this case, this might be things like, I don't know, the distance to the goal, the velocity of the robot, the angular, the orientation, and so on. So the first step, we learn the intrinsic reward, and in the second step, we learn the neural network architecture. So our intrinsic reward is parameterized features, and we initiate population of agents, each with the differently parameterized reward. We train the agents, we evaluate their performance within task objective, whether it completed the task or it did not. And then the mutator proposes the new reward based on the performance of the previous one and spawns a new training agent. And we keep repeating that loop for a while until we find the reward that fits the learning task and makes it tractable. Once we have the reward, we repeat basically the same process for the neural network architectures. So the parameterization here can be the number of layers, the width, and the depth of the networks, and other hyperparameters of the neural network architecture. And again, same process, randomly initiate, train, evaluate, except that this time we're evaluating with respect to the cumulative reward. Propose the new mutation until we're happy and we find the policy. And just as a side note, we also asked how general really is this reward search? Is it working only in navigation, or does it work across the other environments? So we did a benchmarking across several reinforcement learning algorithms and several benchmarking environments. And we found out that reward search helps in more complex tasks. The more complex and difficult task is, the automation works better. The second finding is that it really doesn't make sense to create complex objectives, that the simple sparse here we reach there or go as fast as you can works almost as well without any hand engineering of the skills for the task objective. And finally, we found out that on a fixed training budget, if we're starting with a reasonable hyperparameters, the training budget is better spent on learning the rewards than tuning the hyperparameters of the model. So back to the navigation. So to get the navigation in this zero-shot model working, we first initiate the training in simulation with the noisy sensors, actuators, and kinematic model, basically adding as much noise as we can. And we we randomize initial and goal conditions. These two lead to policies that are resilient to noise on the real robots and are capable of zero shot transfer. And then we train via this automated RL process that use two steps, learning the rewards first and then neural network architecture. And that steps ensures the competency of the system. And then we just use the off-the-shelf algorithm. Once we have the policy, we do zero-shot transfer, and it runs on real environments, even with the people around, or other static environments, and so on. Again, this is reactive policy. It doesn't know why it's getting. It just kind of goes and adapts. The the same methodology works across different robots, and that includes robots with the kinodynamic constraints, with the noisy sensors such as asteroid dynamics and so on, which is basically producing approximate solution to two-point boundary problem. And that's exciting. Now let's look at now into another robot that is also capable of navigation, and this is joint work with UJ's Reddy's lab at Harvard. The this is a crazy fly nano drone that has only 33 kilobytes of available RAM, weighs 33 grams, and costs under $300. How do we train and make this robot autonomous and do something useful? The We train these models on high-end hardware that has GPUs and so on. And then the onboard hardware is Raspberry Pi that is much cheaper and so on. And in fact, when we plot the two trajectories that are run on one and the other hardware, they look very differently, which in this context actually poses safety concern. So to avoid this problem that damaging the robots, we developed air learning, hardware in the loop simulation environment, where it builds on top of AirSim. We can add randomized environments and whatnot to create photorealistic scenes, and then be able to plug in the target processor directly and run policies and evaluate policies on the target processor, even though it's still running in simulation. And that is much safer. And not only that, but we can also observe and calculate the latencies that are resulting from these processors. For example, inference latency on Intel Core i7 is 3 milliseconds, whereas on Raspberry Pi is 68 milliseconds. And we can kind of build into the simulator and train policies on GPUs that are capable of running on Raspberry Pis. So to that end, then, one of the useful applications that we can do is source finding, or in this case, finding a light for the crazy fly, basically building an autonomous moth that if it senses the light and is going to go towards light. And to do that, we equip the quadrotor with a light sensor and the 4 laser readings. We really want the sparse information, so the network needs to be compact to be able to fit on board. And in simulation, basically build a model out of the observing the lights in the environment, and train in simulation using this technique with a hardware in loop, transfers zero shot on the real Crazy Fly Robot. The So we talked about learning control policies here. These are the reactive policies. And we saw that training them in simulation and addressing all the sources of the sim to real gap are enabling us to do a zero shot transfer to a variety of the real world scenarios, and learning hyperparameters of the reinforcement learning models, such as the rewarded neural network architecture and so on, with evolutionary and reinforcement learning together, leads to the competency, increases competency of the policies. And then domain randomization adds the resilience. Now, in the rest of the talk, even though we have these good policies that are promising and so on, they're not going to be perfect. So the question now is how we should place the goals such that not only they're leading to the higher level goal, but they're working with the imperfect policies and they're producing reasonable goals, because that's the other way to how to close this in the real gap. So the idea is, can we practice our control policies that are taking observations, telling robots what to do and interacting with the world, reflect on that experience and get better? So to get to the goal selection policies, basically this is the policy that's going to tell our control policy what to do. And for that, we connected basically that selection policy should also work on the same information that control policy does. So have the same observations, and also should be able to have the access to the prior experience and see how how the robot behaved in the past. And now, once we have that experience, we can practice and collect the data. And via self supervision, we can learn the predictive model that associates the observation now with the future performance of the system, or how the goal is reachable and whatnot. And then in the unseen environments, we can use that model to predict the goal selection. In naive words, for example, I don't need to go and roll out a policy if I see a wall ahead of me to know that I'm going to hit the wall, even though I haven't encountered that particular example before. But something similar happened before, and we can kind of know that that's not. So in the rest of the talk, I'm going to show two examples. One is on cooperative avoidance task, avoiding humans, and the second one is a cooperative rendezvous task. So this is joint work with Claire Tomlin's lab at Berkeley. And what we want here is, how do we do visual navigation around humans? So imagine having a mobile robot, and we want to basically put in any environment around humans and have the robot safely avoid humans and reach the goal. What are the challenges here? This is a CVPR conference. I don't need to tell you that zero shot transfer from simulation to reality with the visual policy is difficult. So one choice is that we just train this in reality on real systems. However, that poses safety risk to humans, and also raises questions of the privacy and diversity of the human subjects. So if we do this in simulation, safety is not a problem. We have a photorealism to deal with, but then privacy and diversity of human data set is probably more manageable. So let's see how we address that. We know that there are data sets of human models, surreal, and we also know that there are data sets of the scanned realistic buildings, 3D, such as Stanford Large 3D Indoor Spaces dataset. And in this case, we combine the two, and we parameterize humans on the scene, that we can place them anywhere in the environment. We can parameterize their gender, we can parameterize their texture, clothing, skin color, facial features, and so on. We can parameterize their body shape, whether they're tall, short, etc., and their motion. Are they moving straight, or they're following different trajectories, and so on. And then we can render what that scene would look like. And that gives us a really nice and rich playground that we can sample a bunch of scenarios and create a data set, avoiding any of the privacy and safety and diversity concerns that we might have had working with real human subjects. So here is an example what the humans placed in this data set look like, or the environment. So how do we go about training? We practice in the known environment, so they're placed in. We randomly generate and place the humans, give them initial poses and behaviors and the goals where they need to go. And then we solve this problem with MPC, which requires knowledge of human trajectories in the environment, but that's okay. This is a training environment, so we know how this is going to roll out. And then to train, we collect a data set where we kind of propose this bunch of waypoints and we evaluate how each one of them does uh, with respect to the rollout policies. And at that point, we associate the visual input with the optimally placed waypoint. So if I see this, this is where I should place the waypoint. Once we have that perception module, we put it in a system, so it receives image, it produces the waypoint goes in a system, and then the controller drives the robot there, and here we go again. And let's see, compared to the baselines that are not trained with humans, we get 80% versus other baselines without humans going under under 70%. And then looking at a couple of other scenarios, we see that, for example, in this case, when the robot is static, this would be the dashed line, the robot actually goes in front of the person. But when a human is moving, that's the red line, it actually goes behind the person. And that's kind of nice. This is the static human, this is the dynamic human. Kind of behind the scenes seems like it kind of learns that the position of the legs is determining the motion and the speed of the human. In the second, compared to the baseline, we see baseline is the dashed line here, that it goes and it cuts off the human, whereas our method, when it's trained with the humans on the scene, actually goes behind nicely. It also, we demonstrated that also, even though it's not trained, it has some ability to handle multiple humans. So in this case, there are two humans on the scene, and the robot kind of goes and weaves between them. So let's see how this looks on the robot. Interesting part here is human is coming, and the robot is going to veer on the right. In simulation, was trained with a camera field of view 60 degrees, and on the robot, the camera field of view is only 45 degrees. And it still transfers, which is interesting. Here's another experiment, and the human is going to come behind the corner, and the robot goes around. In both of these scenarios, the baselines would actually collide with a human. So the second example is a cooperative task that I want to mention today. Let's assume that we have two agents, two robots. They need to meet, perform cooperative tasks. They're not directly communicating with each other. Basically, the only information they have is what they can observe with their sensors, because that's how we coordinate as well. And each one of them is equipped with some control policy, like one of these point-to-point policies, that can be different, and there are no assumptions, or that the planning module does not know anything a priori about it. So the question is, how do we train the models such that they can meet? And the idea is that we propose waypoints that are both feasible to each one of the robots and kind of will drive them towards the meetup. Now, to be able to do that, it would be very useful to have a model that can predict where I am going to be, where ego robot is going to be, and where the other robots are going to be. So FI is a model, ego robot model, that says, okay, here are the observations, and here is where I'm going, and responds with a pose where the robot is going to be in time delta t. And F minus I is model for the other robot. So given what ego robot can observe where the robot teammate is currently and where its thing is going to predict where the robot's going to be in time delta t. So, how do we train these two models? Well, we initiate the simulation environment. We randomly place the robots and randomly place the goals and let them run. And then we observe these trajectories and collect the data set that contains current observations and goal, because that's where they ended. So observation and goal that we're thinking, and where the robot was in time delta t. And that gives us a predictive model of behavior, so we can basically observe and learn how the robots are moving. And here are the loss functions for cell prediction and other prediction model. Not surprisingly, the cell prediction is better because we have better sensor observations. And then the other prediction is also slightly more error, but still working. And then to do the planner, which proposes where the robot should go next, we use model-based RL. Basically, we propose a first goal in the middle between two robots, and then each robot does this separately. So it goes and rolls out how the scenario might look like using the predictive model, and evaluates a bunch of these goals and finds the most promising ones, reduces the region, and finally selects the goal. The other robot does the same thing, and then they kind of keep going toward each other. This transfers zero shot to real world environments as well. And compared to the baselines, both learned and standard planning methods actually drives the robots closer together than the compared methods. So here is an example. This is a COVID special in simulation, but we had the experiments on robots as well. In these scenarios, they meet. This is the baseline. They end up kind of in this local minima where they chase each other. This is another baseline. In this case, again, they actually keep running away from each other. In this scenario, again, they reach each other. And the baseline, again, comes in the local minima and they chase each other. So we covered two examples here about learning the goal selection. On two examples, one on the avoidance and the other one on the cooperative task. In both cases, we can observe the motion and learn predictive models. And then using these predictive models, apply them in new environments. So self-supervision and reinforcement learning together, reinforcement learning is a control policy and self-supervision is a planning policy, lead to the resiliency and competency. So overall, both on the lower level control policies and in the goal selection, we saw that to get robots to have zero shots into real transfer, domain randomization and training environment design, addressing it, all the parts of the sim to real gap due to the robot environment and modeling errors is important. Second thing, we saw that combining evolutionary algorithms with reinforcement learning algorithms leads to better reinforcement learning agents with less engineering. And the evolutionary algorithms automate reinforcement learning agents designed by learning the fixed properties of the system. And finally, self-supervision and reinforcement learning lead to the planning that improves with the experience that is within agents' abilities. So put together in this way, the planner will not propose the goals that are not feasible for the control policy that that a robot actually has. And this is very important for the transfer. And finally, we saw that evolution, reinforcement learning, and self-supervision work together to produce the system that works in practice. What's nice about these things is the better algorithms along each one of these axes actually improves the performance of the entire system. So I presented several techniques here that kind of lead us towards robot navigation in real world at scale. There's many more things that we can be talking about and to look in the future, going towards more complex tasks, different robots, curriculum learning, and so on. But the future is there. And with that, I wanted to thank my collaborators, without whom this would not be possible. And I want to thank you. Thank you.